So in the previous section, we're looking at solving quadratic equations by using the intercepts, so finding our zeros. Here we're going to solve by finding our square roots. So first we want to talk about what a square root is. So if I have something like x equals 25, square that value. So if I have x squared equals 25 and I want to take the x value and get it by itself, I need to go ahead and take the square root. So I'm going to take the square root of the left and the square root of the right. When I do this, there's one very important step we cannot forget, which is that when I take the square root of a value, I'm getting both the positive and the negative. So this is going to be plus or minus 5. That's the biggest thing I see people forgetting in this section here. So when we look at this sign we see here, the sort of like check mark with a little swoop here, is referred to as our radical sign. The thing underneath it is our radicand, and we call the expression itself a radical. So just notation wise, that's what all that stuff means. The reason we have this as plus or minus is because when we think about it, 5 times 5 gives me 25, but negative 5 times negative 5 also gives me 25. So it ends up that I get two solutions for these things. Later on in your math career, we'll see that this is true for all even roots, but we're not quite there yet. So we'll just look at square roots. We can also have square roots for numbers that are not so pretty. So for example, if I were to look at the square root of 7, right? It does not have a nice, even, clean square root. So when I talk about the square root of 7, I know it's going to be between the square root of 9 and the square root of 4. These are nice square roots. So the square root of 4, if I were just talking in terms of simplifying the value, is 2, and in terms of simplifying the value is 3. So when I look at the square root of 7, it's somewhere in between those two values, and we can approximate that, and we can use a calculator to do so. Here we're looking at our properties of square roots. So two properties we want to make sure we are aware of. The first is my product property. So if I have a square root of some product, I can split it out into the square root of the two individual products. And then my quotient property, which is if I have the square root of some fraction, I can split it out and it's going to be the square root of the numerator over the square root of the denominator. So now we're going to look at an example of this below. So as we look at example A here, we see the square root of 24. So I want to know what the square root of 24 is. I think I can simplify this thing. And so if I think I can simplify it, I want to see what factors I have. I'm going to go a little bit of a different route here. And I'm going to say, okay, I got square root 24. I want to create what's referred to as a prime factorization tree. So I'm going to split this thing out into all of its factors. So what makes up 24? Pretty sure I can do 2 and 12. If I do 2 and 12, can I split the 2 any further? Nope, that's a prime number. What about the 12? Can I split that into 2 and 6? And then can I split the 6 again into 2 and 3? Absolutely. So now I've got my prime factorization here. So I'm going to rewrite this as the square root of, and it's going to be really annoying, but I'm writing 2 times 2 times 2 times 3. So put some multiplication signs in between those. There we go. And the thing that I'm looking for is to get outside of this square root, I need to have a square value. So when I have 2 times 2, this could be written as 2 squared. So now I want to think about this thing as I have 2 squared times 2 times 3. Anything that has a square underneath a square root, all these things are being multiplied, is able to come outside. Think about it like this is a force field, right? If this is a force field, you have to sacrifice something to break through the force field. We're going to sacrifice our 2 here, right? So we don't see it written here, but there's actually a little 2 here, which we'll talk about later on in our math careers when we talk about like 4th degree, 6th degree stuff. But for right now, just know that all of these are 2nd degree roots. So this is my root here with a power of 2. I got an exponent here of 2. So this 2 is able to come outside. It loses its square, and then I've got just my remaining square root of 2 times 3, which is just 6. So this thing, root 24, is going to simplify to be 2 root 6. Looking at this example here in orange, I see that I have the square root of 7 over the square root of 16. So I'm going to split this thing up. So I have square root 7 over square root 16. The square root of 16 ends up being a nice number for me. It just ends up being 4, and this is my final answer. The one thing we want to make a special note of is that when we're simplifying these radicals, we only consider it simplified if there is no more radical in the denominator. So again, we can't have any perfect squares underneath the square root, and we can't have any radicals in our denominator. So when I look to this one, I'm done here, but let's look at a slightly different situation. Let's look at D. So for D, I have 7 over 2, so I'm going to split this into root 7 over root 2. The multiplication here is of a clever 1. The clever 1 that we're going to multiply by doesn't change anything, right? That's why we call it a clever 1. It changes the way it looks, but doesn't actually change what the value is. So when I'm looking to multiply by a clever 1, I'm going to look to my denominator to see what is my square root of. So here I have a square root of 2. If I have square root of 2 times the square root of 2, it'll just give me 2. So when I do this, I'm going to multiply by whatever the denominator is, and this is root 2 over root 2 here. So this is going to give me root 14 on top, and then just 2 on the bottom. And then this would be my final answer there. So this is just going through those instructions I just did. So rationalizing our denominator here, so multiplying by root 2 over root 2. When we look at these things, when we're solving, we're actually going to do the plus or minus, but if we're just simplifying, we don't, which is a little bit confusing. I know people get hung up on that. So like when we're doing these, I wouldn't say it's plus or minus root 14 over 2. I would just say it's 14 over 2 because we're just simplifying the expression, which is different than actually solving a quadratic equation. So if I was solving, let's say for example I had like x squared is equal to 7 over 2, then in this instance when I take the square root and take the square root, I would have the plus or minus. And I know that's a little bit confusing, but that's just the difference between solving and simplifying. So solving, we need to put that plus or minus in there because it could be both, but if we're just simplifying, we're just saying, okay, let's reduce it and let's make sure we get rid of all of our radicals in the denominator. Now let's look at another example. This one we're actually solving a full problem. So here we have 2x squared plus 1 equals 17. What I would like to do is get this x thing by itself. So first move is to subtract over or add any other constants. So now I'm left with 2x squared equals 16. From here, I want to multiply or divide whatever I need to do to get x by itself. So I'm going to divide by 2 in this problem. So now I got x squared equals 8. My next move is to get the x by itself. To do so, I'm going to take the square root. So I'm going to take the square root of the right side as well. When I take the square root, we always remember that it's going to be plus or minus the square root of whatever that thing is. And now I want to look to this 8. I look to this 8 and I think, okay, what does it break down into? Pretty sure it breaks down into 2 and 4, which breaks down into 2 and 2. Do I have a pair of 2's or more 2's here? Yes, I do, right? I have at least one pair and then a little bit extra. So I'm going to write this is equal to plus or minus the square root of, not a very good square root, but that's okay. Now I'm going to write this as 2 squared times 2. If I had 2 to the 5th, I would do 2 squared times 2 squared times 2. The reason being is I want to separate everything that I can pull outside of my square root, right? 2 squared can come out as a 2. So my final answer here is going to be plus or minus 2 square root 2. When we look at this, if we plug in these values, which we can approximate for if we want to do that on a calculator, but you can just evaluate for these exact values on a calculator as well. We'll see we get approximately 2.8 and negative 2.8. And when we plug it in, it will spit out the exact 17 there for us. If not, it'll be like, 16.999 or like 17.001 or whatever, however much rounding we did to it. So here we're going to solve another quadratic equation. So this is just showing us an example just using the graph. So we're just skipping the graph on this one. But if you want to graph this, more than welcome to. We know this thing has a vertex at -5, -7 if we subtracted this over and then did the y equal stuff. So here we're just looking at where it's going to equal 7. So in this instance, this is our y value, which can be a little bit confusing. So I'll say that one more time. If I were to say this is just some general equation, it would be y equals 1/3, then we got x plus 5 squared. And now here we're saying is going to be equal to 7. So if I wanted to say, okay, well then I want to set this to a 0 by doing -7, you can solve like that, but we're going to end up bringing the 7 over anyways. So just like FYI, that's what I was just referencing a second ago there. So when we look at this thing, I'll say, okay, now I want it, instead of equaling y, I have a specific value that I want, and that specific value is 7. So I want to know when this thing is equal to 7. So if I were to do a super quick graph of this thing, just for curiosity's sake here, the vertex is going to be at -5, 0, and it's going to open up wide, basically. So this thing is going to more or less look like this, and then we're going to figure out wherever, x, or y value is 7. So we're going to have a line that comes through, and we'll have 2 answers here and here, or that's what we should hopefully see at least. So now as we go through this thing, we want to solve it. The first step I'm going to do to solving is I want to get the whole chunk by itself. Okay, so when I look at the thing being squared, that is what I want to get by itself. To get that by itself, I'm going to multiply both sides by 3. So I'm going to say, okay, I get now x plus 5 squared, whoops, not a very good 2, equal to 21, because I multiplied both sides by 3. 3 times 1/3 just cancels off. 7 times 3 gives me 21. From here, now I'm going to take my square root. So let's take our square root, take our square root. We get x plus 5 equals plus or minus the square root of 21. There's nothing I can do to simplify 21. It's just 7 times 3, so there's nothing I can do. Here now I look at my last step. The last step is to get x by itself. To get x by itself, I'm going to subtract 5 and subtract 5. So my x value equals -5 plus or minus the square root of 21. Don't approximate that. Leave that as your final answer. That is good to go. So we can write this out as -5 plus square root 21 and -5 minus square root 21, but that's more writing. I'm incredibly lazy. I don't want to write it out twice, so I'll just do the -5 plus or minus square root 21. Totally acceptable answer there. Here we're looking at a real-life example. So here we have our equation for height of a dropped object. So basically, as I drop something, it starts shooting to the ground faster and faster. It will obviously reach a terminal velocity at a certain point, so that terminal velocity just means this thing can't fall any faster. It's the reason why if I, had an ant along with the air resistance, the ant wouldn't just die if it fell from a building, right? So ant hits the ground, walks away, keeps on living its best ant life. If I have something bigger though, where it can reach a higher terminal velocity and is not going to get the same air resistance, then I'm good to go. So again, feather versus bowling ball versus marble, very, very similar there. So now as I look at this thing, I'm saying, okay, well, what is it? Well, what it's telling me is the height of an object at time t is equal to -16 times t squared plus h sub 0. H sub 0 is the starting height, whereas h is the height at time t. So I'm going to write that out. So h is the height at time t, h sub 0 is my starting height. So we will eventually get to a point where we're going to also include velocity in this. So like if I threw the thing up or if I threw the thing down, but for right now we're just going to start with this basic equation. So when I look at this, I'm going to be told some information. Either I'm told the starting height, or I'm told the ending height, or I'm told the time, and then I'm going to solve for whatever one is missing. So we're going to be missing basically one piece, and we're going to solve for the rest. Let's look at this. So copied our equation down here for us. We'll highlight the relevant information. We have 100 feet above the ground is where this stunt guy is going to fall from a window, so can help by drawing a picture. Here we have our building. Here's the window. There is our little stunt dude with his little stunt face. And now we have a stated height here of 100. He's going to jump down to a cushion, which is 26 feet wide, which is not important to me, but it is 30 feet long, also not important to me, but it is also 9 feet high. That is important to me. So, I mean, I guess it's important that I don't want him to like miss the cushion, but in general, I'm really concerned with height here. So 9 feet high. So I'm going to draw a little stunt cushion here, the height of which is 9 feet. So as I look at this thing, he's going to go from 100 feet to hit the cushion at 9 feet. So his initial height is 100. And then when he hits the bottom, that's going to be at 9 feet above the ground. So here, we're going to say how long before he reaches the cushion. So let's set up our equation. So we're going to fill in the value. So the value he's going to end at is going to end at the cushion, which is 9. I don't know how long it's going to take him. That's how I'm setting the problem up, is to solve for my t value. But I do know that he started at 100 feet. So now in order to solve this thing, I'm going to subtract 100 from both sides. Oops. There we go. So I get negative 91 equals negative 16t squared. I'm going to divide both sides by negative 16 here. This does not look like something I can simplify, and you'd be correct in thinking that. My negatives are going to cancel off though, and now I get 91 over 16 equals t squared. My last move here is to take the square root, take the square root. So my answer now, I'm just going to scroll down a little bit, is going to be that t equals 91 over 16. There's our root. Can't forget the plus or minus anytime I take a square root. But in this instance, we have reality bumping against us. Is he a time traveler? I'm going to assume not. So he's not going back in time. There are some questions where we would include a positive and a negative, but for this, it's just going to be limited by the fact that we only are going forward in time. So this is going to just turn into the square root of 91 over 16, and it's only positive. So again, just keep in mind that that's for this problem. Other problems, it does have an applicable instance, but for this one, it does not. Now I want to simplify this thing. Remember, I don't want a radical in my denominator. So my t value equals root 91 over root 16. And root 16 happens to be one of those nice ones, so it's a perfect square. So this thing will just turn into root 91 over 4. This is how long it would take for him to hit the ground. So again, we can do a calculation and look at this thing and just say, well, root 91 is like a little bit less than 10. You know, 10 divided by 4 is 2.5, so it's going to be a little less than 2.5 seconds. And when we do our approximation with the calculator, it comes out to be approximately 2.4. Pretty close. The next bit is talking about, I'll go back up here. So it's saying that a movie camera operating at 24 frames per second Stuntman's fall here. How many frames of film will show during him falling? So now I'm basically just taking my 2.4 and multiplying by 24. So that's the last bit here. Approximation from our previous answer times 24 equals about 57 frames. That is it for 5.3.